Hello everyone. In this session, I'm going to introduce you to the concept of random forest. Today, random forest is one of the important machine learning algorithms, or I'll say the processes, which is used widely over the concept of decision trees. It has replaced the decision trees in a large number of scenarios. And what are these random forests? The word is very clear. One is it's a forest. Forest itself means it's a group of trees, and those trees are formed in a random fashion. So, from the data, we are going to generate not one single decision tree, but a big ensemble of trees, and they are generated randomly, and they would do the process of making the decisions from the data. So let's get more and more details of the same. Basically, the introductory aspect, we are not using R in this session. We are not using any kind of tools to understand this in this session. From the next session onwards, I'm going to take up a data set and I'm going to explain you the various concepts of random forest using the data sets. So here we'll have a quick introduction of what is random forest, why should we really use random forests, how are they really better compared to let's say a decision trees or any other machine learning algorithms. So we will be talking about that introductory aspect. Then one of the outshoots of the random forest, which is the random ferns, what are they altogether? How are they used in the industry? For what purposes they are typically used? So we will be looking at random ferns, and we will look at what is the key difference that is existing between the decision trees, which you already have a good amount of understanding of, and random ferns, which we are going to introduce in the upcoming session. Just think of a very simple example. Just read through the first few bullet points, and based on that I'll do a detailed explanation of random forests. Let's think of a scenario where we have a sample of size n. Let's say we have looked at the diabetes data. I hope by now you are aware of the diabetes data which we have been dealing for our various applications. So it has 600 records altogether, but after removing the NAs we had around 564 records. Okay, so we are talking about a sample of size 564 and M features. There are 6 features which are predicting whether the person is having diabetes or not. There was a feature called age, we had a feature called glucose levels, right? We had pressure, the pregnancy, the month of pregnancy, etc. So we have a sample of size 564 and 6 features. Now what the random forests do is, it's just not one single decision tree. They build multiple decision trees out of this. If I have to predict whether the person is having diabetes or not, the random forest build multiple decision trees, and each tree is grown from different set of training data. So out of this 564, let's say I have broken down 400 as a training data and the remaining 164 as a testing data. What the random forests do is, out of this 400, different sets of this 400, different subsets of this 400 are typically taken. Right? Different subsets of this 400 are being taken, different sets of training data. Different sets of this 400 are typically taken, and multiple decision trees are created, not just one single decision tree. So for each tree that we are building, K training samples are randomly selected. So probably from here, let's say 250 or 300 random samples are randomly selected with replacement. So there is a possibility that the same thing can occur again and again. There is a possibility that some observations may not occur at all from this original training data set. So there is a set of 300 observations that are being taken out of this 400 data in such a way that there is a replacement with a random selection. Now, at every decision node, because it's a tree, we are talking about at every decision node, the splitting feature, right? In a decision tree, at every node, the splitting happens based on one single variable, which is the best out of all the variables that are available. Whereas here, the scenario is slightly different. Even the features wise also, though it has 6 features, probably it will randomly select some 3 features. Out of the 6 features that are there to select from, it can randomly select only 3 features. So subspace of M features. So we are out of the 6, it is talking of 3 features, where this 3 is much smaller than the total number of features 6. So the tree is built, the first tree might be built with one set of 3 features, the second tree is built with some other set of 3 features. So different sets of features are typically being used, different combinations of features are being used to build the trees, and a different number of trees are built. It's just not one single tree, multiple trees are built, which means there is a possibility of multiple decisions coming out, and to sort out those decisions, there is a voting process that is being performed. So each tree that is getting built, let's say with a subset of this 6, let's say with only based on 3 variables, this tree is grown to whatever the largest extent possible. The tree is not pruned here. So like this, let's say I can instruct for it to create some 1000 different trees, where two things are happening here. If my data set is training set data is 400 records, so randomly some 300 records will be chosen, and this would be with replacement. So there is a possibility of duplication in the values, there is a possibility of a few values getting completely ignored. So that's one aspect in random trees, random forests. The second aspect is, let's say there are 6 features which are used to build a tree, 6 attributes which are used to build a tree. Again, a very small subset of the features, let's say 2 or 3 features are selected at random, and based on that the tree is being built. So every tree has a different set of 2 or 3 features, which means sometimes some of the variables which may get completely ignored in when we are talking about 6 variable scenario, here it might not be the case at all. There is a possibility that almost all the variables will be included as a part of our selection process. Each tree, there is no pruning of the tree that is performed. Each tree is grown to the largest extent possible. Then, now we have, let's say, 100,000 such kind of trees that are built. Now, when I have to classify a new object, so each tree, we have 1000 trees. So for a new data, which is test data 1, each of the 1000 trees will do a prediction. So will it belong to default category or non-default category, default, or will it become in the diabetes example, whether the person is having diabetes or no diabetes, whether the person is positive to diabetes or negative to diabetes. So each tree will do the prediction, of whether the person is positive to diabetes or negative to diabetes. So there is a kind of a voting. So this tree goes for a negative, this tree goes for a negative, this tree goes for a negative, this tree goes for a positive. So finally, the prediction is the majority. Now in this case, there are 3 trees that are going for negative, whereas only 1 tree is going for positive out of the 4 trees. But I would have created 1,000 such kind of trees. Now based on that 1,000 trees, I can really assess which one is more preferred, which one is more voted by almost all the trees. And based on the majority, the final prediction class for that particular observation is typically coming out. Now here if we see why these random forests are more preferred compared to decision trees. Two things. If you look at each decision tree that is being built, one, it is built with a smaller subset of data out of 400. It is taking only 300 or something. The subset of data with which it is building the forest is a smaller set, and even the features that it is using is also smaller. So which means theoretically when I compare it with a decision tree which is built with a higher set of data as well as higher number of features, obviously should be more and more effective compared to the tree that is built in the random forest. Agreed. That is perfectly true. Each tree, if I look at one tree in isolation in a random forest, it is less accurate because one, it is building the model with a less number of sample. Along with that, it's also building the tree with a less number of features, a subset of features. So obviously, the accuracy of the tree that is a part of the random forest is less accurate compared to a classical decision tree. But here we are not building one single tree, remember, we are building thousands of trees. Now what happens is we are trying to combine all the 1,000 predictions into one single aggregate prediction. So all 1,000 combinations, different sizes, different trees, different variables used to build the tree. So that way what is happening is we are able to combine multiple predictions into one single accurate prediction, which we are expecting that it should be more and more accurate prediction compared to just looking at one decision tree in isolation. So it is the typical way of putting it is there are so many weak learners. Each tree I can call it as a weak learner. But if I am putting 100 weak learners into a group where each one has learnt one single aspect and all the 100 are coming together as a group for taking a decision, probably the combined knowledge of these 100 weak learners is much higher compared to one single strong learner. Now that is what is the concept behind the building of random forest. So we are talking of average of many trees. We are talking about thousands of trees that are being built. In case there is no correlation between the trees, means each one is actually bringing in a different dimension. Each tree is built based on a new definition of the variables, new dimension of the variables. Then they are all bringing some new knowledge into the overall process. And because of that, some new information that is coming up, when I'm aggregating all of them, that is not getting sensitive to noise, rather it is increasing the accuracy of the model. So what has been understood is overall variance is drastically reduced when we are going with random forests. There is an increase in the accuracy, there is a decrease in the overall variance, and the bias relating to one single decision tree. In case of one single decision tree, the variables that are used for building the tree, there might be a bias in the splitting of the tree. Whereas here, because we are doing that same activity n number of times, that bias is also going off overall in the selection process. Now that is the reason today for various decisions people are preferring the random forest rather than the traditional classification trees, decision trees kind of models. Now a slightly different outshoot from this random forest is the random ferns. Here we are talking about constrained trees. It's again an ensemble of constrained trees. So tree is a much bigger one. When you talk about ferns, they are much smaller. That's the simple concept out here. We are building an ensemble of constrained trees. If there is no constraint, we are calling it as a random forest. Whereas when there are a lot of constraints in terms of building the trees, we are calling them as random ferns. There is a heavy usage of that in the image processing field, where we are identifying textured patches. See, if I'm having an image, there are patches. I'm looking at small parts of the image. So here, some kind of textures that are existing. We are trying to identify the texture patches surrounding the key points of interest. Let's say there is a face out here, and I want to look at some kind of patches that are there around this face, especially if the image is taken from multiple viewpoints. Now, typically people have used this concept of random ferns very heavily in that particular process, where they are trying to compare the patches that are existing, especially when the photograph is taken from multiple perspectives. Some of the things, because of the constraints that are being put, one, they are extremely fast, and they are obviously outperforming the random forests, because random forest the tree is grown to an unlimited depth, whereas here there is a lot of constraint workout in terms of growing of the tree. They are much easier to implement. So especially for image processing, people have really found random ferns to be much a better option even compared to the random forest. But the only limitation that we see in the usage of random fern is the training data set should be as large as possible. We cannot do it with 100 elements of training data or 500 elements of the training data. The training data set should be much larger. Nowadays we are talking about the world of big data, so probably providing the training data sets would never be a constraint. But remember, every business has a data which is unique to its business. So in some cases it may be very difficult in terms of collecting huge volumes of data, but wherever we have a big set of data that is available, probably I can very well use random ferns again for decision making purposes. So here the major difference is the same decision function for each node. So when I am talking about a tree at different levels, right, I am talking about a tree that is operating at different levels. Now in case of fern, what is happening is, so we are talking about these are the nodes at this level. The same decision function is applied to both the nodes. Now coming here, again the same decision function, which might be different from this. At this layer, again it's the same decision function that is applied at each node for this level. So that is a systematic application at a fern level. The whole data is getting split, but again the same decision function is being applied at each of the nodes which are lying at the same level. So each fern, it is consisting of small set of binary tests, right? It's a decision taking kind of stuff, greater than something or less than something. So it's a small set of binary tests that are run, and the output wise we are getting a probability that a particular record is belonging to either the default either the diabetes class or the no diabetes kind of a class. So we are looking at every fern having a few set of binary tests, and based on the binary tests it will return the probability that a particular record or a particular object belongs to or that a particular person will belong to the category diabetes or will not belong to the category diabetes. So that is how the random ferns are going to work. When we take up examples on the data sets, things will become more clear. But just giving you a very brief conceptual overview of the topic so that you can appreciate them when we are starting to work on the data per se. So when you are talking about collating all the probabilities, a naive Bayesian approach is used, and finally based on the collation of the probabilities, it would be finally classified whether it would be falling into a diabetes group or a non-diabetes group. So the classification happens based on the usage of naive Bayesian approach on all the various effective probabilities that are getting built from each of the ferns. So in decision trees, the binary tests are organized hierarchically. There is a hierarchical decision tree. Whereas we are talking about in case of ferns, everything is flat because the same decision is being applied for each node at each level. So the ferns are more or less flatter. I don't need, in case of trees, if I have to grow 2 to the power of n leaves like this, I require 2 to the power of n minus 1 operators. Now if you see here, if I have to grow a tree like this, I need one rule out here and I also need one rule out here. So I need operators wise 1, 2, 3 operators are being worked out. So overall I am getting, if I have to grow 4 leaves, so if my leaves are 2 to the power of 2, I require 2 to the power of 2 minus 1 operations, which is 2 operations are typically required, one here and one at this layer. Whereas when we are talking about 2 power n leaves in case of a fern, because the decision that is applied is uniform across each layer, so I need one decision here, I need one decision here. Whereas in case of trees, that is not the case. If I have to grow 2 to the power of n leaves, so here if I have to grow 2 cube leaves, I require 2 to the power of 3 minus 1, which is 2 to the power of 2. 4 operations are very much required to grow 8 leaves there, whereas here I require only 3 operations to grow 2 to the power of n leaves. For each layer I need only one operation. So that's one advantage. So even because the same decision is being flatly applied across all the nodes for a particular level. When it comes to the fern, we have already discussed it is containing a small set of binary tests, and output wise it returns the probability that a particular observation belongs to either group 1 or group 2 based on the learning that has been done during the learning phase. So in case of decision trees, the posterior distribution, which is in terms of the output after the 1,000 trees have typically done the prediction part, the posterior distribution, they are computed additively, which means they are simply added up. Their weightages are typically, their classifications are typically considered, and the majority voting is simply contributed. So the posterior distributions are simply computed additive, whereas in case of ferns, it is coming out to be more and more multiplicative. So that's the reason we could see that there are various aspects where the random ferns are much appropriate and much more sophisticated compared to the decision trees. And once we start using our data sets, working them with various packages of R, we would be clearly in a position to make out the differences between the random ferns and the decision trees for the same data set for the same business objective. right? So just get a basic overview of the same, and once when we start getting working out with the data sets, things become more and more clearer to you. So that's what I wanted to look at in this very introductory session. If you have any further queries, please feel free to get in touch with me, giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@hisgurus.com. Thanks a lot for listening to this session. Thank you very much.